Dear ladies and gentlemen, welcome to this presentation. I will speak about joint processing of DS and PS used to investigate complex surface displacements over the storage cavern field at Epe. The storage cavern field at Epe has been pried out of the lower Rhine salt flat and is used for the storage of natural gas, helium, brine and petroleum. Our project partners supported us with information about the storage site, leveling data and groundwater level measurements. We observed three phenomena that superpose: linear subsidence caused by convergence of the caverns, displacement responding to pressure changes in the gas-filled caverns, a seasonal hydraulic movement over a fan. Anticipating results, you see here for ascending and descending orbits the deformation fields for each of these three components. For this work, a modified version of stamps was used that allows processing PS and DS jointly and makes use of a three-component phase model able to describe the just mentioned three phenomena. We used Sentinel-1 data from ascending and descending orbit and calculated from them vertical and east-west movements separately for the three named components. Findings are validated with ground truth from leveling and groundwater level measurements. On this slide, you see the linear component of displacement in line of sight for descending orbit. In the area where the gas caverns are situated, a cyclic signal is superposed to the linear subsidence. On this slide, you see the pressure-induced signal, which is confined to the area with gas-filled caverns. The observed detrended displacements show that the cyclic signal displays a time shift versus the filling levels. In order to derive a model, we assumed that each cavern is a pressure source in a sphere of salt, that the viscoelastic response of the salt modifies the pressure signal inside the cavern to a pressure signal on the surface of the salt sphere, according to this formula derived for a Kelvin-Voigt body, and that the elastic behavior of the overburden transfers the signal on the surface of the salt sphere to the surface of the Earth without further delay. The unknown parameter eta over E was found by minimizing the difference between data observed in a preliminary analysis and the parameterized model curve. Likewise, a model for the displacements of the fan has been extracted from a preliminary INSA analysis. The diagram shows the median deformation over the fan, the derived model, and for comparison, the groundwater levels from one of the measurements at the edge of the fan. The points found on the fan are all distributed scatterers. On the right you see a Google Earth image of the fan. A question is if the points on the fan provide information on the other components of the displacement field. As you can see, is the linear component clearly visible over the fan. On this slide, the vertical and horizontal displacement corresponding to linear convergence are displayed. The horizontal movement is towards the center of subsidence. A similar behavior can be observed for the pressure-induced displacement. The hydraulic displacement over the fan shows no significant east-west movement. The comparison of linear trends estimated from leveling and from INSA shows a good agreement. Above, a histogram of the differences, below their spatial arrangement. Thank you for your attention.